going to do lesson 11-2, exponential functions, and talk about a couple of different kinds of functions that we can have. One in the form y equals b to the x power, where b is a variable, so some variable, whatever that may be, and x is a real number. That's called a power function. And so you can see we have an example here, y equals x to the fifth, where the base is an exponent, or the base is a variable and our exponent 5 is a real number. Our next function is in the same form, y equals b to the x, but this time b, or the base, is a real number and x is a variable, and that's called an exponential function. And it's in the form y equals 3 to the x. There's an example of that one. Any function for the following form has the given property. So the form we're talking about is f of x equals a to the x. That's again just a different way of writing the exponential function. F of x, remember, is y, and this time our base is represented by an a being some real number. And in this case, a is going to be greater than 0, or a positive number. The properties depend on the value of a. So if a is equal to 1, then we end up with a horizontal line, and the equation is just going to be y equals 1. And that's because 1 to any exponent, or any power, is just 1. So what happens if it's something other than 1, but still a positive number? So that's when we look at these two options, and one being where a is between 0 and 1. So a is greater than 0 and less than 1. So we're looking at a decimal. If a is between 0 and 1, the general form of the function is going to go down from left to right. And so we say that as x increases, y decreases or heads to 0. And as x decreases, y increases and goes to infinity. And it has a horizontal asymptote at y equals 0, which is your x-axis there. The other function is where a is greater than 1. And for those values, the shape of the graph goes up from left to right. For this one, as x increases, y goes to infinity, or y increases, and as x decreases, y, or f of x, heads to 0. And again, we have a horizontal asymptote of y equals 0, or the x-axis. So I want to take a look at a graph of some different exponential functions, and we'll look and see what happens there with those. For the first one, we're going to graph y equals 4 to the x power. And to do that, if you want to use your graphing calculator or Desmos, that's perfectly fine. So for the first one, I'm going to graph y equals 4 to the x power. And that's going to look like this. Hopefully yours looks a little bit better than mine. And then for the second one, we've got y equals 4x plus 2. It's going to be a similar graph, but we're just going to go up 2 units on the plane. So something like this. And then the third one comes down. And you got to hear my phone go off. So I think you can see from the graphs that it's the same graph, but it's just because we added, on the second one we added 2, so the whole graph went up 2 units, and on the third one when we subtracted 3, the whole graph went down 3 units. All right, for part B, similar kind of problem. The graphs are going to look a little bit different though, because we've got 1/5 instead of a whole number to the x power. So for the first one, we have y equals 1/5 to the x power, and that's going to look like something like this. And then the third one times 6, so and then on the third one, we've got a -2 times 1/5 to the x. That negative is going to make it reflect across the x-axis, and it looks like this. All right, for the one that's marked number 5, it's not an equation, but it's an inequality. So you need to think about what that means. If it's a less than or greater than sign, it's going to be a dotted line. If it's a less than or equal to or greater than or equal to, it's going to be a solid line. And then we're going to have some shading. So for this particular one, instead of drawing a solid line when we graph it, this one's going to have a dotted line. And it's going to take the shape this shape here, and then since y is less than 2 to the x plus 1, we're going to shade below for that one. So that's what an inequality would look like. Okay, on the next page, we're going to talk about what it means in terms of a word problem or an application. When a quantity loses value over time, the value exhibits what's called exponential decay. So when something goes down over time. And then when something gains value over time, that's called exponential growth. So sometimes we can take both of these and use an example of a population where, like in a small city, small town, over time, the population tends to go down, people move away, so that would be an example of exponential decay. Whereas where they're moving, like to the large city, that could be an example of exponential growth, is where over time the population increases in a large city. All right, we've got a fun little example here of exponential growth and decay. We actually have a little formula, and the formula is n equals n sub 0 times 1 plus r to the t power. N is the final amount, so the value that we want to get in the end. N sub 0 is the initial amount, so whatever we start with. R is the rate of either growth or decay, depending on the situation, per time period. So it'll be growth or decay per year or week or second or some time period. And then T is the number of those time periods. And that's used to model exponential growth or decay. So we're going to use that particular function. So we have n equals n sub 0 times 1 plus r to the t power. It says, suppose that a researcher estimates that the initial population of bees in the colony is 500. They are increasing at a rate of 14% per week. What is the expected population in 22 weeks? So n is the thing we want to know, the expected population. We don't know that one yet. N sub 0 is the initial number. Well, we know that the initial population of the bees was 500. The rate, now that's the rate per time period. So the rate is 14%, and I already went ahead and changed it to a decimal, that 14% to 0.14 per week. And the expected population, what's the expected population in 22 weeks? So that's our time, which is 22 weeks. All you're going to do is fill this equation in, just like we see it. So we want to find n. N sub 0 is 500 times 1 plus whatever r is, which is 0.14, and t was 22. And you can really just put that in your calculator on its own, or you can also do the order of operations, but what you should end up is n is approximately 8,931 bees. All right, we have one more fun application here, and this is about money, talking about making compound interest. And we have a formula for that. A equals P times 1 plus R over N to the N times T power. So you're going to multiply N and T to get the exponent there. P is your principal or initial investment. It's kind of like N sub 0 in the last problem. A is the final amount of the investment, so that's what you're going to get at the end. R is the annual interest rate. N is the number of times the interest is paid. So sometimes it can be paid annually, which is once a year. Semi-annually is twice a year. Quarterly would be 4 times. Just depends. You kind of have to pay attention to the problem. And T is the number of years that we're going to pay. So we're going to write down our formula. A equals P times 1 plus R over N to the N times T. We want to find out what A is here. It says determine the amount of money in a money market account providing an annual rate of 5% compound daily if Marcus invested $200,000 and left it in the account for 7 years. So the principal is the initial investment. He invested, I think I said $200,000. That's $2,000. The rate is 5%, so 0.05, and it's important to note that that was compounded daily. So every day of the year, the rate was compounded 5%, so we added more and more on. And N, which is the number of times the interest is paid, if it was compounded daily,
I gotta use your turlet.
all right, somehow I lost the whole problem there. So I'm going to back up. Hopefully you can see that we're going to use that equation. It says determine the amount of money in a money market account providing an annual rate of 5% compounded daily if Marcus invested $2,000 and left it in the account for 7 years. So we've got A equals, and that's the final amount that you make, equals P, which is the principal there, or the initial investment, times 1 plus R, which is the rate. N is the number of times the interest is paid, and then T is going to be the number of time in years, so T years. So we want to find out what A is for this problem. The principal is the original amount invested, and that was $2,000. And Let's see, the rate is 5%. I'm going to go ahead and change it to a decimal, 0.05. And it's important to note that that's compounded daily. N is the number of times the interest is paid, and because it's compounded daily, there are 365 days in a year. Because we always think about that as in years. And then T is the number of years we do that, and that for this one that's 7 years. And you want to fill in your equation. So my equation is going to look like A equals 2,000 times 1 plus 0.05 over 365 to the, and then n times t. So that's going to be 365 times 7. So when you do that as an exponent, that 365 times 7 all has to stay together. Again, you can use the order of operations, or you can just put it in your calculator all at once, but you should get an amount of $2,838.07.